Hi, in this video I will show you how the adder will be used as a building block in our ALU project. I will increase the bit size a bit, we will go to 16 bits, but most of the things that I will show you in Circuitverse you already realized by yourself, in some cases as part of an exercise. So you can think of these parts in this video where I show you things in Circuitverse as kind of a review, or in case you didn't have enough time to solve all the exercises, work on all these exercises as a catch-up opportunity. So you just can use then these things from now on as building block for the rest of the project. In the end of the video I will also show you how the so-called status flags that our adder will set after each computation can be used in our computer for realizing conditional jumps. Some of the features that we provide are not new. You already know that we can use the adder for also doing subtraction, and increasing the bit size from 8 bits to 16 bits is not a big deal. We will also store the result in some register, so that after a computation we can copy the result into some other register, or we could copy it to memory. You also know that we have these bits, these flags, indicating whether we had an overflow. And actually for that we have already two flags, depending on whether we indicate an unsigned overflow or signed overflow. What will be kind of new is the so-called zero flag, which indicates that all the bits in the result are 0, and the signed flag, which indicates that the most significant bit is 1, which means if we want to do some operation with signed integers, it would indicate that the result is negative. So this is the initial setup for our 16-bit adder. We have two input devices with 16 bits, one output device with 16 bits, and a bit for switching from add to sub. Now I will not use the adder that we created. I will just for convenience use the adder from Circuitverse, but of course you can use our adder as well, built on full adders and half adders. Now let me first set up things so that I can do addition and subtraction. So I need here a 16-bit NOT gate connected with a multiplexer here. Also changed to 16 bits. Now here I either get the inverted bit pattern of B or the bit pattern of B as it is, and use this for the adder. And with this bit I switch between addition and subtraction. If I'm doing addition, then I just get the bit pattern of B, otherwise the inverted bit pattern, and also Cin is in case of addition 0 and otherwise 1. And then we already can test things like that. Then we can do addition and subtraction. The next thing is I will use this register for storing the result. For realizing a register we use this flip-flop here. Change it also to 16 bits. And then I also need a clock, and each time the clock is on 1 I want to copy the result into this register. So I'm just disconnecting things here. Connect it with the clock and also show this here. But actually you see that we don't have to look at this output device anymore, because in Circuitverse we also can see it here. Now let's do some operation, and each time I turn the clock on, the result gets copied into this register. Okay, the next thing is we already can add some status flags, for example the carry flag and the overflow flag. The carry flag is what we get here, a cout, so should have moved this a bit more to the right. So we'll just connect this cout with an output device and call it CF. For the overflow flag, I need a subcircuit and actually two subcircuits, or it's convenient to have two subcircuits. One subcircuit for getting the sign of a input, and the other one then implementing these rules for the actual computation of the overflow. So the subcircuit SF we will also use for the sign flag. So already nice to give it the right name. So this is the input A with 16 bits, and I want to pick up the most significant bit, so I use the splitter, splitting 16 bits into 15 and the most significant bit. And here I of course should change it to 16, like that. And then I need one output bit. Which is then the sign. And because I want to use it as a subcircuit, slim and slick, let's change the layout like that. Okay, then the next subcircuit, the overflow flag. Here I have three 16-bit inputs. So this is A, and I need the same for B and S. Here we go. And then I also need an input to change between add and sub. I just need the signs of A, B and S. So I use this subcircuit 3 times. And then I can implement the rules for the overflow flag. Let's begin with the case where we do some addition. Then the rule would be, or one part of the rule would be, if A and B is negative and S is not negative. So that means I need another AND gate and also this NOT gate. Then we already have one of two reasons why an addition could overflow. The second reason would be that A and B were non-negative. So I'm using another AND with 2 NOTs. So this means A and B were non-negative, and we have an overflow if S is then in this case negative. So this handles the two cases, and if one of them is true, we have an overflow. And we also can test this here. So this is the overflow flag. For example, negative, negative result is non-negative, gives an overflow. Now, in case of a subtraction, we actually can reuse this circuit. We simply have to invert the bit pattern of B before we pick up its sign. And then basically we get the inverted sign of B and can map this new case of a subtraction to the case of an addition. And I will do this in a quick and ugly way. I simply use here a multiplexer with 16 bits. And this multiplexer either gets the bit pattern of, uses the, or delegates the bit pattern of B or the inverted bit pattern of B. In case of a subtraction, the inverted bit pattern. So this inverter goes down here, says 16 bits. And with this bit I'm doing the selection. And then this wire goes back. Okay. And then of course you should check that the math also works in this practical application. Okay, but now we can use these building blocks for getting the sign flag and the overflow flag for our 16-bit adder. Now, and then we already can add some status bits. So we need the sign flag and we need the overflow flag. For the sign flag, I just pick up the result from the accumulator. So I should pick it up after it's in the accumulator. Or we pick up whatever we have in the accumulator. And maybe I already connect here the output device and give it a label so that I don't forget. So this is the sign flag, and here I want to compute the overflow flag for signed integer. And here I connect this S with the result stored in the register here, A and B with the input devices, A and B. And this add, I need somehow to connect with that. So this will not be nice because I have to cross a few lines. But I think you get the idea. And that's almost it. Now I just need a new circuit for computing also this 0 flag. And for that I first use this 16-bit input device called A, and then I first check whether one of these bits is 1 and with an OR gate or with OR gates, and then negate the result. When you use these OR gates, you also can increase the input size, but only up to 10. And you also see that it's not looking nice if you use more than 4 of them. So I will use a bunch of these OR gates with 4-bit input devices. First I check the bits in groups of 4. And for that I split this 16 inputs into groups of 4. 16 gets split into 4, 4, 4, 4. No. And then again I split 4 bits into 1, 1, 1 and 1. And of that I also need 4 splitters. Now this is a point where you regret that we increased the bit size to 16 bits, but it's just a matter of effort to do this. Okay, so here I check whether this first group has a bit equal to 1. And in the same fashion we can check the remaining groups. Okay, done. And now I check with another 4 input OR gate whether one of these groups caught one. And then negate the result. And this gives us the 0 flag. So it's 1 if all bits are 0. And here we also can make this a slick and slim building block like that. And then we can add this to the 16-bit adder. Okay, let's save that. Now for testing it, I want to create a demo circle, and for that I will use again the 16 segment displays for showing a plus or a minus sign, depending on whether we do an addition or subtraction. Let me just prepare that and show you the result. You already saw in the previous video how to use this 16 segment display to show either a minus or a plus sign, together with this constant input fields and this multiplexer. And I'm using this in this demo for showing the sign depending on whether we are doing an addition or a subtraction. And now you can use this demo to see that, first of all, after clicking the clock, if you change the operands, the computed result gets displayed, the bit pattern represented with 4 hex displays. And here you can validate whether the status flags are correctly set. And using this demo will be useful for the next thing when I show you how conditional jumps are realized depending on this status flags. The control flow of programs written in machine code or assembly code can be visualized with flowcharts, like here for example. And in this graphical notation that I use for these flowcharts, a rectangle, for example, always represents one machine instruction that does not influence the control flow. That means it's not a jump instruction. And for the jump instructions, I always use these diamond-shaped symbols. And you know that jumps can come in 2 flavors. We have these unconditional jumps, which are also realized with one single instruction, and these conditional jumps. And for these conditional jumps, I will write within this diamond-shaped symbol some condition. This will always be a single, simple condition. So we don't have some logical AND or conjunction. And all these conditional jumps have in common that you realize them with 2 instructions. It's always a subtraction followed by a check for certain status flags. And depending on whether certain conditions are met, you carry out the jump or not. So for example, if you check for equality, you first subtract the left and right hand side from each other and then check whether the 0 flag is set or not. And if it's set, you do the jump. On the website you can find this table with all the conditions that can be used in these conditional jumps. And the first 2 cases are very simple. The jump is supposed to be carried out depending on whether 2 values are equal or not. And in these cases, you don't have to distinguish whether the values are unsigned or signed values. In both cases, you first do the subtraction, and after that, you check the 0 flag. In these tables, you also see these phrases like, for example, jump equal, jump not equal. Later, when we will use assembly code instead of directly writing programs in machine code, we will use these phrases together with this so-called assembly mnemonics. So this is already kind of a preparation for what is coming ahead. In all the other conditions, we have some relation, like for example, A is smaller than B. And then we do have to distinguish between two cases. The first case, that A and B is unsigned, and the second case, that A and B is signed. Now here I first want to leave it to you as an exercise to validate this table, and then I want to discuss this table with you in class.